Today, we're exploring the weirdest aircraft ever built and the unbelievable stories behind them. Started with number 1, Christmas Bullet, United States, 1918. Dr. William Whitney Christmas built the Bullet around a single radical idea. Wings with no external bracing struts at all, designed to flex in flight the way a bird's wings do. No wind tunnel testing, no structural stress analysis, no static load testing preceded construction. According to account from the period, the very first flight ended when the wings folded backward and sheared off midair, killing the test pilot. A second aircraft reportedly suffered the same fate on its own first flight. Aviation historians have since questioned parts of Christmas's own account of the program, noting inconsistencies and a documented pattern of exaggerated claims from the designer himself. But the surviving record still stands as a case study in what happens when an engineer trusts theory over testing. The Bullet never received production order, never proved its concept, and became remembered less for what it achieved and more as a warning about skipping the fundamentals of aircraft design entirely. Number 2, Caproni CA-60 Transaereo, Italy, 1921. Giovanni Battista Caproni imagined a flying boat that could carry 100 passengers across the Atlantic, and to generate enough lift for that weight, he stacked 9 wings in 3 sets of triplanes along the fuselage, powered by 8 engines. The design broke from every convention of the era, betting that sheer wing area could substitute for aerodynamic refinement. On its first taxi test, the aircraft lifted briefly off Lake Maggiore, encouraging enough for a second attempt. That second flight ended when the structure broke apart in the air roughly 60 feet above the water, sending the hull crashing down and destroying the aircraft beyond repair. No one was seriously hurt, but the transatlantic airliner dream died with it. The CA-60 never flew again. No successor was built. And the project stands as one of the clearest lessons in early aviation that adding more wings does not solve the underlying problem of stability at scale. Number 3, Westland Pterodactyl MKV, United Kingdom, 1934. Long before flying wings became a serious military pursuit, Westland engineer Geoffrey Hill was convinced that removing the tail entirely could eliminate the stall and spin accidents that killed so many pilots of the era. His tailless, swept-wing pterodactyl series culminated in the MKV, a 2-seat fighter prototype with a rear-firing gun position built into a design nobody else in Britain was willing to attempt. It flew, and it did resist the vicious spins that plagued conventional aircraft at the time, proving Hill's underlying theory correct. But stability came at the cost of control response that test pilots found sluggish and unfamiliar, and the Air Ministry, already committed to conventional fighter programs, saw no compelling reason to retool production around an improving configuration. Only a handful of pterodactyls were ever built. The design vanished from British service, but the questions it raised about tailless stability would resurface a decade later in Germany, on a far larger and far deadlier scale. Number 4, Stipa Caproni, Italy, 1932. Luigi Stipa's design looked less like an airplane and more like a flying barrel, because that was almost exactly what was: a hollow tube-shaped fuselage with the engine and propeller mounted inside, using the tube itself as a duct to accelerate airflow, an idea decades ahead of the duct fan and early jet engine concepts anticipated. Skeptics assumed the barrel shape would create crippling drag and that the aircraft would barely move. Instead, it flew, and flew with remarkable stability, exactly as Stipa's calculations predicted. The problem was not whether it worked, but what it was good for. The heavy tube added weight the airframe could not spare. Top speed remained low, and the pilot's forward visibility was badly compromised by the surrounding duct. No military application justified the trade-offs, and the design was shelved as an academic curiosity rather than a combat aircraft, even as its underlying principle quietly influenced later thinking about duct propulsion. Number 5, Tupolev ANT-20 Maxim Gorky, Soviet Union, 1934. Built as a flagship of Soviet aviation propaganda, the 8-engine ANT-20 was, at the time, the largest land-based aircraft in the world, designed to carry journalists, loudspeakers, and even a printing press as a flying symbol of Soviet industrial power. Its sheer scale demanded compromises no other aircraft of the era faced, including wings so large that a small escort fighter could safely fly in close formation beside it for propaganda newsreel footage. During one such flyby in 1935, the escort pilot attempted a risky aerobatic maneuver near the giant aircraft and struck the Maxim Gorky's wing, shearing off structure and sending both aircraft down. All aboard were killed in what remains one of the deadliest aviation disasters of the interwar period. The tragedy exposed the danger of treating a giant aircraft as a stunt prop rather than a fragile, unforgiving machine its size actually made it, and no second Maxim Gorky was ever completed to the same standard. Number 6. Kalinin K-7, Soviet Union, 1933. Konstantin Kalinin's K-7 was conceived as both a heavy bomber and a mass troop transport, built around a giant flying wing configuration with twin tail booms. Fixed landing gear housed an enormous drag-inducing pods, and has many as 7 engines mounted along the leading edge. The scale of the aircraft outran the engineering tools available to analyze it, and the tail booms in particular suffered from severe structural vibration that engineers of the time struggled to fully understand or correct. During a test flight in November 1933, that vibration triggered a catastrophic tail failure, sending the aircraft into ground and killing 14 of the people aboard. Soviet authorities pressed forward briefly with plans for an even larger successor, but the fatal crash effectively ended serious development. The K-7 became a cautionary tale about designing at a scale beyond what contemporary structural analysis could reliably predict, a problem that will recur in giant aircraft programs for decades afterward. Number 7. Blériot Zapata 125, France, 1931. René Zapata's design for the Blériot company paired 2 separate fuselages joined by a shared wing and tail structure, with passengers and crew split between the twin hulls, an attempt to distribute weight and offer redundancy that no conventional single fuselage airliner could match. In practice, the twin-body layout introduced handling problems that outweighed any theoretical benefit, with test pilots reporting the aircraft was difficult to keep coordinated in turns and demanding to fly compared to conventional designs of similar size. Structural complexity also drove costs well beyond what airlines of the era were willing to accept for an improving configuration. No production order ever materialized, and the sole prototype was quietly retired without ever entering service. The Blériot 125 demonstrated a lesson that would echo through decades of twin fuselage experiments to come. Joining 2 aircraft together rarely solves a problem as cleanly on paper as it does in the workshop. 8. Blohm and Voss BV-141, Germany, 1938. Chief designer Richard Voigt built the BV-141 around a single unconventional decision. Instead of centering the crew compartment on the aircraft's axis, he moved it entirely to one side, mounting the engines separately on the opposite boom to give observers an unobstructed view in every direction, essential for its intended reconnaissance role. The asymmetry looked wrong to nearly everyone who saw it, and Luftwaffe officials repeatedly hesitated to approve full production despite test results showing the aircraft handled predictably and performed its observation mission well. That institutional skepticism, rooted almost entirely in the aircraft's unfamiliar silhouette rather than any genuine flaw, meant the more conventional twin-boom Focke-Wulf FW-189 was chosen instead for large-scale production. Only a small number of BV-141s were ever built, making it a rare case of an aircraft failing not because the engineering was wrong, but because it looked too strange for decision-makers to trust. Number 9. Vought V-173, Flying Pancake, United States, 1942. Charles Zimmerman's near-circular flying wing was built around a theory that a disc-shaped airframe could achieve both extremely low landing speeds and, with the right engines, extremely high top speeds, a combination that seemed contradictory to most aerodynamicists of the era. In testing, the disc shape genuinely delivered the low-speed stability Zimmerman promised, with the aircraft able to fly and land at speeds that would stall a conventional fighter. The problem was propulsion. The underpowered piston engines available never came close to unlocking the high-speed performance the theory predicted, and by the time a more powerful armed successor, the XF-5U, was ready for testing, jet engines had already made the entire piston-powered concept obsolete before it ever reached combat. The Navy canceled the program and reportedly had the completed XF-5U prototypes destroyed rather than preserved, ending one of the most genuinely original American fighter concepts of the war, without it ever firing a shot. Number 10. Northrop N-1M, United States, 1940. Jack Northrop's obsession with eliminating the fuselage and tail entirely began with the N-1M, a small, low-powered testbed built purely to prove that a flying wing could sustain controlled flight. Early test flights exposed real instability, with pilots reporting the aircraft was difficult to control in anything but calm conditions, and the underpowered engine suffered chronic overheating that limited how long any single test could last. Rather than abandon the concept, Northrop's team spent years modifying the N-1M's wing shape and control surfaces, treating every failure as data rather than defeat. That patient, iterative testing eventually produced the aerodynamic understanding behind Northrop's much larger YB-35 and YB-49 flying wing bombers later in the decade. The N-1M itself never became a combat aircraft and was never meant to be one, but without its rough, unstable early flights, the flying wing concept might never have matured into a credible military design at all. Number 11, Miles Libellula, United Kingdom, 1942. George Miles designed a Libellula around a tandem wing layout, placing a second lifting wing near the nose instead of conventional tail, aiming to give carrier pilots a clearer view over the nose during landing and to reduce the stall risk that made deck landings so dangerous. Small-scale prototypes demonstrated that the underlying principle worked, with the forward wing genuinely improving visibility during the critical landing approach. But the tandem arrangement also introduced complex interactions between the two wings that made the aircraft more difficult to balance and trim than a conventional design, and naval authorities were unwilling to commit carrier fighter production to an unfamiliar configuration in the middle of a war. The Libellula never advanced beyond experimental prototypes, and Miles moved on to more conventional projects, leaving the tandem wing idea as an intriguing but ultimately unrealized answer to a real and dangerous problem in naval aviation. Number 12, Curtiss-Wright XP-55 Ascender, United States, 1943. Built backward by conventional standards, the Ascender places propeller behind the pilot in a pusher configuration and its small control surfaces on a forward canard instead of rear tail, earning pilots' grim nickname Ascender for its reverse silhouette. The canard layout promised to eliminate the torque and propeller wash problems of conventional fighters, but it came with a lethal flaw. Once the aircraft entered spin, the canard surfaces lost effectiveness and pilots found the aircraft nearly impossible to recover using standard techniques. That flaw proved fatal during a public demonstration flight, when the aircraft entered an uncontrollable spin and crashed, killing the test pilot in front of onlookers. Combined a performance that failed to significantly outclass conventional fighters already in production, the disaster ended any realistic chance of an order. The Ascender became a textbook example of how an elegant solution to one problem can quietly create a far more dangerous one. Number 13, Northrop XP-56 Black Bullet, United States, 1943. Built almost entirely from magnesium to save weight, the disc-shaped XP-56 dispensed with a tail fin altogether, relying on a pusher propeller and small wingtip rudders for directional control, an arrangement that looked sleek on paper but proved treacherous on the runway. Without a conventional tail to provide directional stability during takeoff, the aircraft ground looped violently on its very first flight attempt, damaging the airframe before it had even properly flown. A rebuilt second prototype fared little better, suffering an in-flight control failure that forced the test pilot to bail out to survive. Northrop's engineers had correctly predicted the aerodynamic benefits of removing the tail, but underestimated how much control authority pilots would lose on the ground, where the aircraft actually needed to operate most of the time. The Army Air Forces canceled the program, and the Black Bullet became a cautionary example of a design that solved for the air while ignoring the runway. Number 14, Volti XP 54 Swiss Goose, United States, 1943. The XP-54's most unusual feature was hidden inside the cockpit rather than on its twin-boom pusher airframe, an ejectable seat system that could raise or lower the pilot's position to help him withstand high-G maneuvers and improve his chances of escaping in an emergency, a genuinely forward-thinking safety idea for its time. But the aircraft was designed around a powerful new engine that never became available in time, forcing Volti to substitute a weaker, less reliable power plant that left the finished prototype badly underperforming its original specifications. Flight Testing revealed sluggish climb rates and disappointing top speed that could not compete with more conventional fighters already reaching squadrons. With the engine problem never resolved and the war's fighter requirements shifting rapidly, the Army Air Forces canceled the program before it left the prototype stage, leaving the XP-54's genuinely innovative safety features as a footnote to an airframe that never received the power it needed to matter. Number 15, Fisher P-75 Eagle, United States, 1943. Under pressure to field a fast-climbing interceptor quickly, General Motors Fisher Body Division assembled the P-75 from components borrowed from several existing aircraft, including outer wing panels drawn from Mustang production, in an effort to shortcut development by reusing proven parts. The shortcut backfired. Combining mismatched components from different aircraft designs created handling characteristics engineers had not properly modeled, and early test flights revealed serious control and structural problems that led to a string of crashes, several of them fatal to test pilots. By the time those flaws were being worked through, the specific mission the Eagle had been rushed to fill, long-range escort for B-29 bombers, had already been solved by extended-range P-51 Mustangs performing far better than the P-75 ever achieved. The program was canceled after roughly a dozen prototypes, a costly demonstration that assembling a new aircraft from borrowed parts does not guarantee it inherits any of their reliability. Number 16, Arado AR-232 Tatzelwurm, Germany, 1941. Nicknamed Tatzelwurm, after a mythical centipede-like creature, the AR-232 transport carried an extra row of small wheels running beneath its main fuselage in addition to its conventional landing gear, allowing it to taxi and take off from rough, unprepared airstrips that would have wrecked a normal transport's undercarriage. The additional wheels could even be used to help the aircraft crouch low to ground for easier loading of vehicles and cargo without ground equipment. That capability came at a real aerodynamic cost, since the extra wheel assemblies added drag and weight that reduced overall performance compared to conventional transports. Despite the odd appearance, the concept worked as intended in the field, giving German forces a genuinely capable rough field transport at a time when suitable airstrips were increasingly scarce. Production remained limited by wartime material shortages rather than any flaw in the design itself, and only a small number ever reached operational units before the war ended. Number 17, Junkers Ju-322 Mammoth, Germany, 1941. Designed as a massive flying wing glider capable of carrying tanks and heavy vehicles for a planned invasion of Britain, the Ju-322 was built largely from wood due to wartime shortages of aircraft-grade metal, a material substitution that undermined the entire concept from the start. The finished aircraft came in dramatically overweight, its center of gravity badly miscalculated for the cargo it was meant to carry, and control response proved sluggish and unpredictable even for an unpowered glider. During testing, the aircraft struggled to become properly airborne even under tow, and loading a tank inside shifted the balance so severely that the design was judged effectively unusable for its intended purpose. With the invasion of Britain already shelled by the time testing concluded, the program was abandoned outright, and a handful of completed airframes were scrapped or repurposed as lumber, making the Mammoth one of the most complete engineering failures of the entire war. Number 18, Messerschmitt Me 323 Gigant, Germany, 1941. Developed as a powered evolution of the enormous Me-321 glider, the six-engine Gigant became one of the largest land-based transport of the war, capable of hauling tanks, artillery, and dozens of troops in a single lift. Its sheer size made takeoff a genuine engineering problem, often requiring rocket-assisted boosters or additional tow aircraft simply to get airborne with a full load. Once flying, the Gigant was painfully slow and only lightly armed for its size, making it acutely vulnerable whenever fighter escort was unavailable. That vulnerability turned catastrophic during Allied fighter sweeps over the Mediterranean in 1943, when unescorted formations of Gigants were caught in the open and shot down in large numbers within minutes. Some of the heaviest single-day transport losses of the war. The aircraft could carry almost anything the German army needed moved, but only if enemy fighters were nowhere near, a condition that grew rarer as the war went on. Number 19, Heinkel He-111Z Zwilling, Germany, 1942. Faced with shortage of aircraft powerful enough to tow the giant Me-321 glider, Heinkel engineers took the unusual step of joining two complete U-111 bomber fuselages together with a new center wing section and a fifth engine, creating a genuine twin-bodied aircraft rather than a symmetrical new design. The resulting Zwilling worked, generating enough combined power to successfully tow the massive glider into the air, but the airframe carried real structural strain from forces the original single fuselage U-111 had never been designed to handle. Only a small number, roughly a dozen, were ever built, limiting their operational footprint from the start. Once the Power Me-323 Gigant entered service and no longer needed a dedicated tow aircraft, the Zwilling's narrow purpose largely disappeared, leaving it remembered less for combat achievements and more as a striking example of wartime improvisation, solving one urgent problem for a very short time. Number 20 Blohm and Voss BV-238, Germany, 1944. The largest aircraft built by any Axis power during the war, the six-engine BV-238 was designed as a long-range maritime patrol, flying boat capable of covering vast stretches of ocean that smaller aircraft could never reach. Its immense size demanded enormous engineering resources at a point in the war when Germany could least afford them, and only a single prototype was ever completed. That prototype never had the chance to prove itself in the role it was built for. While moored on a lake awaiting further testing, it was spotted and strafed by American fighters, which set it ablaze and destroyed it before it ever flew an operational mission. The BV-238 became a symbol of the late-war German pattern of pouring scarce resources into ambitious, oversized projects that consumed enormous effort but delivered nothing to the war effort. Sunk not by any flaw in its design, but by the war closing around it before it could finish. Number 21 McDonnell XF-85 Goblin, United States, 1948. Built to solve the problem of defending long-range B-36 bombers too far from any friendly airfield for escort fighters to reach. The tiny Goblin was designed to be carried inside the bomber's bomb bay and released mid-flight to intercept threats before returning to dock with a trapeze mechanism and be hauled back aboard. The launch worked reliably enough in testing, but redocking proved to be an extraordinarily difficult task, requiring the Goblin's pilot to precisely match speed and position with a much larger aircraft while being buffeted by turbulent air trailing behind the bomber. Several docking attempts damaged the small fighter, and on one occasion the pilot narrowly avoided serious injury when the aircraft struck the trapeze hard enough to crack the canopy. As aerial refueling technology matured and made genuine long-range escort fighters practical, the entire parasite fighter concept lost its purpose, and the program was quietly canceled without the Goblin ever reaching operational units. Number 22 Convair XFY Pogo, United States, 1954. The Pogo was built to take off and land standing straight up on its tail, powered by a propeller engine strong enough to hold the entire aircraft vertical against gravity before tilting into forward flight, a solution meant to let fighters operate from small ships or forward areas without a runway. Climbing away vertically proved to be the easier half of the problem. Landing required the pilot to descend tail first while looking back over his own shoulder to judge height and position above the ground, an extraordinarily disorienting task with almost no room for error. Only one pilot, company test pilot James Fitzpatrick, ever managed to complete a full vertical takeoff and landing in the same flight, and even that success came only after extensive practice most operational pilots would never have had time for. The Navy concluded the landing technique was simply too demanding for routine fleet use, and the program was canceled without ever reaching production. Number 23 Lockheed XFV Salmon, United States, 1954. Developed alongside the Pogo as a parallel attempt at a tail-sitting vertical takeoff fighter for small ship decks, the XFV shared the same fundamental ambition, but never actually managed to demonstrate a genuine vertical takeoff or landing during its entire test program. Instead, Lockheed fitted the prototype with a temporary, non-retractable landing gear. So to fly conventional runway tests, while engineers tried to work out the aircraft's vertical flight handling in safer stages. Those tests exposed the same core problem facing the Pogo, a pilot forced to judge a tail-first vertical descent almost entirely by feel and rearward glances, with no reliable instrumentation of the era able to make the task genuinely safe. With the Navy already growing skeptical after watching the Pogo program struggle with the identical challenge, The XFE was canceled before ever attempting the vertical landing it had been built to prove was possible.